Recording. Recording start. Okay, now you can start.
Okay. Hello everyone. I'm Zarif and I'm graduate student in AMOD at Trent University. And today I will talk about multi-word comparison swap, in short MCAS, which is a way to update multiple memory location or a set of data without using log. So for our presentation today, I will at first make some examples using logs to update double linked list using log. And then I will discuss the same thing using compare and swap operation. And then finally, I will talk how can we use multi-word compare and swap operation to do the things better in concurrent environment. So So here is a typical double linked list we can see here where we have a few nodes. Actually, here we have 3 nodes and they are connected with each other back and forth. And this is the main advantage of double linked is that we can traverse forward and both backward. Now, what is a node in our double linked list? A node has 3 elements. The one is the previous pointer that holds the address for the previous node. If there is none, so then we hold actually null pointer. And then this is the data that will hold or store the actual value. And this is the next pointer that will store the address for the next node. Now, this is a simple code that is written for to define a node. And here we can see we have the 3 elements like the data, the next pointer, and the previous pointer. And this is the constructor. Now, what operations that we can do in our double linked list? We can do a few of the operations, like we can do insertion, deletion, forward traversal, backward traversal, and also the searching. But for our purpose today, we will talk about the insertion process. So here you can see we can do the insertion in double linked list in many ways. We can do it before the list, we can do end of the list, we can do any specific reference like before a node or after a node or any specific position. And in our today's example, we will insert a new node after any reference node. Now let's see how can we do the insertion in a double linked list. Suppose, for example, we are trying to include a new node after this node B. So that means my node B is my current node. So we can say this one is my current node, and here is my new node X that I want to insert between B and C, or we can say like after B. So how can we do that? At first, we have to update the pointer of the new node, and we have to connect update this one to B and C. So that is, this previous pointer is holding now B, and this next pointer of X is holding C. And my next step is to update the next pointer of B to X instead of C. The same thing for the C previous. So if I do the same thing for C, I'm going to update this one from B to X. So now this is my new double linked list, and this is a very simple way to update double linked list with a new node. So that is, we are inserting a new node here. Now, what is the problem here? So if we are working on a multi-threaded environment, so we may have problem. Like we have many threads here, and they are trying to insert a new node after B. So what will happen in our concurrent or multi-threaded environment? That it will create a race condition. So to solve this problem, one way is that we can use log. We can log the nodes, and then we can insert the new node in between of B and C. So let's see how can we do that. So for example, here is our double linked list again, and the first step can be we can log our node B, and then we can log our node C. Now any other threads cannot access it, right? And at this point, I can update the list with the new node without any impact of other nodes, without any race condition here. And finally, we can unlock both of these nodes. And now my list is updated, and we have completed our insert operation. So here is a simple code that we can see. We can use to update the double linked list with our new node. And here are some advantages, like we can ensure the consistency. We can implement these one very easily. So these are some advantages. Now, what is the disadvantage here? So the first disadvantage we can say, like when we are locking these nodes, we are blocking this process. So other threads cannot work. So this can be sometimes expensive because we are blocking and we are wasting our time. The other thing is it can also cause deadlock. For example, if we lock B at first and C in one thread, but some other thread is trying to do the same thing in different order, like if it locks C first and then B, so it can cause a deadlock. So we can avoid this one if we follow a specific order for the locking process. Now, to solve this problem, we can, yes.
How can we detect the deadlock? So how do you know does the deadlock happen during your insert multiple thread insert operation?
So
How do you know that's a deadlock?
So the deadlock can happen when we see, like if they are locking in different way, and if we see like when we are trying to lock B and then if we try to lock the C, and if we see the C is already locked by some other threads.
Not really. So detect the deadlock in C or C++. There's no way to detect deadlock. Only you can say is a program, the thread is stopped and no progress.
Yeah.
But in Golang, the deadlock is the exception. So even if C is locked, C is locked by thread 1, but thread 2 want to lock C, it not means the deadlock.
Okay.
Deadlock means like lock cycles happen. So that's a deadlock.
Okay.
So we can design a mechanism to detect these lock cycles. So yeah, in your algorithm, you can implement to check these lock cycles.
Okay. Yeah, we didn't go that far because our purpose is MCAS, so that's fine.
Yes, good. Go on.
So one way to implement a lock-free algorithm is to use the CAS, the compare and swap operation, which is lock-free. So in our multiple threads, we can update them without using lock. Now we will see how CAS works. So in a process CAS, at first we need to read the current value of a specific memory location. And then we will do a check, like if the location is holding my expected value. If I find like, okay, it's holding the expected value, then we will update this one. If we see like it's not holding the expected value, then we have to keep retry. So that means it can generate like retry overhead, the CAS operation. Now, this is a simple function of CAS operation, and we can see in this function is holding 3 parameters. One is the memory location, the old expected value, and the new value. So at this point, we will check if our memory location is holding our expected value. If it is not, so we have to return false, and maybe we can go for a loop to retry. And if it is holding the expected old value, then we can update this one with the new value atomically, and we can say the process is complete. Now here is some fact about the CAS. So the CAS is atomic primitive and it's hardware supported. Like we can find instruction set for in the machine, in the CPU, like in Intel, in AMD, or in ARM processor. And this CAS provided by many and this CAS can be atomic because it performs the whole operation atomically or indivisibly. Now let's see an example how CAS works in Intel 86 architecture. So you can see this is an instruction, lock, compare, exchange, and it holds the destination operand, and this is the source operand. Now, why we have lock as prefix?
The question, well, yes, lock. What's the meaning of lock?
Yeah, why we have this prefix lock before the compare exchange instruction? So this prefix is to lock the bus when we are updating the destination. So this is not actually locking the memory location, but it's locking the bus.
What is a bus?
Sorry?
What is a bus?
This is the connection. This is the connection, interconnection between the memory locations.
Yes, connect the memory location, connect the memory to the CPUs.
Yeah.
Lock that is not lock the.
It's not locking the memory. Yeah.
That lock the bus.
Yeah.
It's more efficient than lock the memory.
Yes.
Good.
So if you want to read more about this, you can read the book written by Silversters on page number 266 to 269. Now let's see a little bit about this instruction, how this instruction works. So here is a typical register set we can see in 86 architecture. So if I have a sentence like I like blue, and if I want to update this blue with red word, so we can think about think in this way. Like suppose I have the instruction move EX and memory location, so it will place the current memory location value in EAX register, and then it will load the new value to EDX register, and then it will perform this CAS operation, the compare exchange, and it will check like if the memory location is still holding the blue. If it still holds the blue and it matched with the EX, because we just have placed the blue in EX register. So if it matched, so then we will update this one with my new value from EDX. Otherwise, we will do nothing, or you will have to keep retry using the loops. Now, this is another example what we can see in ARM architecture. So in ARM architecture, they don't have any built-in CAS operation, but we have a set of instructions that we can use, like the load lock or the store conditional, to do the same thing. So these actually work as a set to do the same thing like the CAS operation. So in previous ARM 8.1 or the previous version, we don't have the built-in CAS operation. So actually, we use these operations for that.
Oh, question.
Yes.
Back, yeah. No.
Yeah.
Come back, but ARM architecture, does it need to lock the bus? Lock the bus.
Yes.
Does it need to lock the bus?
We didn't go that far, but I think so.
No, it doesn't need to lock the bus because it's a retry and fail. So it's not a one instruction. It's a bunch of the load and store. It's a bunch of instructions, and the hardware can detect between the retry and fail. It does that interleaving other threads interleaves in that section. If the interleaves happens, it will cause the retry. Cause the retry. So that's not lock the bus. That's a totally different implementation in hardware level. Okay, this is details of tactics.
Okay.
It's not atomic instructions, right?
Yeah, no. It's just checking before it's updated.
It's a retry and fail to detect the other threads interleaving in this section or not.
Yeah.
But it is implemented by hardware, not software. Hardware.
Yes.
Good.
Now.
Still on one thing. The pass and load and store are equivalent or not?
In ARM architecture, they are mostly equivalent.
Although I said that both architectures are both implementation, they are equivalent or not equivalent?
Equivalent.
They are equivalent because lots of papers already prove that they are equivalent.
Yeah.
So we can treat that as CAS and this one is equivalent. If we can implement with CAS, we can simply implement with load and store. It's not a problem.
Okay.
Not a problem. Go on. Good.
Okay. Now, this is the latest version for the ARM architecture, like ARM 8.1 or the latest version. We have the built-in instruction set for the machines, like CAS or CAS-A or the other variants that we can use to do the same thing. If you want to read more about this, you can go on the ARM Developer 2024 version, this reference, to know more about this CAS operation in ARM architecture. Now, what are some applications of CAS? So, of course, the first application is we can use it in confined programming to implement lock-free algorithms, and several algorithms or the structure we can implement, like we can make lock-free stack, lock-free queue, lock-free doubly linked list that we were seeing, and we can also implement lock-free hash map. Now, let's see how can we use CAS to implement a lock-free insertion process in our doubly linked list. So at first, we can read a given node or the current current node in my W linked list, that is B. And then here we have the new node. And now we need to update all of these 4 pointers, like the previous and next pointer of X, next pointer of B, and the previous pointer of C, all of these 4 using CAS operation. Maybe you can think about this code here to do this process. Here we are updating the next pointer of B using a CAS operation, and we are checking if is there any next node exist here. If there is a next node, if it is not null pointer, so that means we have to update the previous pointer of C. So we are updating this one here. But we also have to update the previous and the next pointer of X.
But the question, why all of your CAS put it to the while loop? Means try.
So because we have to keep retrying if the process is not successful.
Yes, good.
Yeah. So what do you think if this code is correct? Or what do you think, like if we write 2 more loops to update the previous and next pointer of X, will this one be correct?
It's great. It's correct.
Oh, we've answered this one. It's not.
Like my question is like here we can see this one is updating the next pointer of B. This one is updating the previous pointer of C. So if we write more codes, maybe I can update the previous pointer of X and next pointer of X. So even if I write more codes, will this one be correct? Will we succeed to update all of these 4 pointers in this way? In concurrent environment.
Why?
Oh, what if something else is trying to update those from different locations? So like if we try to insert something before.
Yeah, thank you. So now, we are not updating them atomically, right? So this can cause problem. So this can lead to inconsistency as well. Although there is a work that where Sandil and Seegers, they have shown like we can solve this problem and we can ensure their consistency, but still it's a tremendous process and it's very hard or difficult to implement and use. Now that's why we are thinking about a more efficient or advanced way to update all of these 4 pointers together. And that is where we are trying to use the multi-word compare and swap. If we go on the work of Boribui, so then we can understand more about the MCAS and the efficiency of MCAS. Now let's see some advantages of CAS. The one advantage that we can say like it's lock free, so it's not blocking anything, and there is no possible deadlock. But still we have some disadvantages. The first disadvantage is that like it can work for a single word or single memory location, not for multiple memory location, and it has the retry overhead. Now let's talk about the MCAS. The MCAS actually extends the CAS, so we can update multiple memory location atomically, and it's obviously lock-free implementation like the CAS. Now, how MCAS works? MCAS works in a simple 4 steps. The first step is it reads all the values in the memory locations, and then it checks if all the values are matched with the expected values, like my expected value set. And then if all of the value match with the expected with the memory locations, then we will update all of them together atomically. We should not update them partially. We have to update all or none. Now, here is a simple MCAS function. You can see here there is an MCAS descriptor, which was the address and the expected value and the new values. And here we will pass the set of set of values or the tuples that is a collection of address, expected values, and new values. And we have to loop through. We have to check if all of the expected values are matching with the address. If any one of them is not matching, we have to return false. Otherwise, if all of them are matched, so then we can start the swap process, like our CAS process is actually happening here.
Oh, that was just a pseudo code.
Yes.
Implementation should be lock-free and topic.
Yeah, it's just a basic pseudocode just to give the theme about the MCAS. Now, let's see how can we use the MCAS. How can we think about MCAS in our W linked list to insert a new node? Now, here again we have the new node X. So at first we need to read all of the pointers that of the affected nodes. like the next pointer of B, previous of C, and previous next of X. Now we will check if all of them are holding the expected values. Like if the connection, we are expecting the previous and next of null pointer should be null pointer for X, the B next should hold C, and previous of C should hold B. So something like that. If all of these values are matching with the expected values, then we can update all of them atomically using the MCAS process together. We should not update this list partially. If we update this one partially, we can end up with a broken list. So this is the theme of the MCAS to update the linked list with a new node or to insert a new node. So this is another simple pseudocode to use the MCAS process. So you can see this MCAS is actually holding 4 caches here. So this one is to update the B next pointer with X, like this one. We can see the X previous, like this previous, we are going to update this one with B. So if it's holding the null pointer, we should update this one with B. The same thing for the next pointer of X and the previous pointer of C.
Great.
So if any one of them is failed, so then we have to keep retrying this process. So this is some advantages is like it atomically update across multiple pointers and it's lock free. There is no deadlock, no thread blocking, and it also simplifies and ensures consistency. But still, we have the disadvantage that it's hard to implement, and the more problem is like it's not hardware supported directly. So we have to implement this one logically or as programming. Now let's explore the work of Zarif, where we can understand how MCAS can help and how efficient is this one and how MCAS is working. So in my here is my contribution. I have explained like how MCAS work in using diagrams, so we can easily understand this MCAS process. So suppose, for example, in our memory, we have 3 memory locations, 1001, 1002, and 1003, which is holding some values like apple, banana, and cherry. And we want to update this one with some new values, say for example, mango, orange, and grape. So we have to make sure like all of these updates will happen together or fully. It should not update the memory location partially. So in our MCAS process, we have to create a descriptor at first. So here is my descriptor that is created in 3000 location, and here it is holding a field status. The status can be of one of the 3 values, like it can be active, it can be successful, and it can be failed. If we denote this one with 1, we can say it's active. If we denote this one by 2, we can say, for example, it's successful, and 3 for fail. So for now, as we are just starting this process, let's say this one status is active or 1. The n equals to 3 here, that means like we are going to update 3 locations of the 3 values. So that's why our n is 3, and these are the word descriptor that should hold the set of old values, the new values, and the addresses. Now this table is holding the word descriptors. So we can see we have 3 word descriptors at 2001 to 2003 locations, and they are also holding the old values, new values, and the parent addresses. So these are the tuples that we will use to update my current memory location. And this course can be useful to think about this.
What is the parent address?
So parent address is holding the address of the descriptor table.
Good.
Okay. Now the first step is to acquire all of this memory location. So we are trying to loop through these initial values, and we will update them with my word descriptor pointer. So here is my table, the word descriptor table, and here is my MCAS descriptor table. So we can see the status is active, and my n equals to 3. Now, if we run this statement here, we are trying to read at this location, it should hold apple, and if it holds apple, then we can update this on 2001 pointer using this cache operation. So this is my first cache that I'm using, and if it's successful, we can see this is successful, right? So we can go for the next step to update the banana with a new new word descriptor pointer to 2002. And the same thing for the third one, the cherry. If we run the third cache, then we can update this cherry with the new word descriptor pointer. So when my all of these steps are successful, so that means I have successfully completed all of my claiming process. So when this process is done, we can update this. We can think about this, that new table is now holding C.
Why the values are replaced with the descriptor? Why we must use a CAS?
So we need to ensure the atomicity here. So when we are seeing like it's, for example, this third operation. So at this memory location we are running CAS to make sure like it atomically updates the cherry with the new word descriptor. So when it's updated, and if in future when some other thread will come here, if it try to read this one, it will see there is a word descriptor, and it will go in this table. And if the status is success, then it will pick the new value.
Good.
We'll see this one in our next slide. Now, when all of them are updated, so that means we don't have the previous table anymore. It's now holding these descriptors instead of the values. Now we also need to update the MCAS descriptor table with the new status like the successful. So now let's see what will happen if we try to read this one at this point. So now you can see my memory locations is now holding the word descriptor pointers, and the status is successful. So if some thread is trying to read the first memory, for example 1001, it will come here and it will see there is a word descriptor. So when it will see a word descriptor, then it will check the parent 3000 MCAS descriptor table. So it will see what is the status of this table. So it will see like the status is successful. So when it will see the status is successful, it will go on this word descriptor table, and it will pick the new value like the mango as the value for this 1001 location. But if it say like the status is active, then it will go for the old value. So this is a simple code that we can think about it for this read process. If we just think about the highlighted codes, so we can see if it is not a word descriptor, so then we should read the old value in the table. Say for example, maybe it's holding still the cherry in third location. But if it is a word descriptor, then we have to check the parent status. If it is successful, then we will read the new value. And we will explore more about this course in our next slides. Now, let's talk about the deferred memory reclamation process. So when my process is done, we are thinking about, okay, we should reclaim the memory because we don't need this word descriptor anymore. We should update this on all of them with the new values, and we can get rid of these tables. So this is the deferred memory location reclamation process that we are going to see here. So at this point, when my CPU has some free time or another MCAS process is called, so then we can reclaim the memory. So we can reclaim the memory location like 2001, this pointer, we can update this one with mango. We can update this one 2002 with the orange, and the third one with red. So here we are running another 3 CAS to reclaim the memory. So these are some separate things that we can do when we have some lazy time in our CPU. And another case, okay. So here is the table that is updated with the new values, and when it's done, we can safely free the memory or safely reclaim the memory for the descriptor tables. Now, what will happen if some process fails when we are trying to do MCAS process? So, for example, if we are succeeded to complete this, the first CAS operation to update the apple with the new word descriptor, so that's fine. But when we are trying to update the banana with the new value like orange, maybe we can get failed for some reason, like may have been changed by others. So if this happens, we have to abort the process, and we can update the table status as well. So in next retry, maybe calling another MCAS, we can update the process again.
Oh, this is rollback. Fail means rollback.
Yeah.
Do it again.
Yeah. So here is a very simple flowchart that can be used to understand the total MCAS process. The first step is to acquire or claim the memory location, and the second step is to check like if all of these memory locations was claimed, if all of them was matched and we were succeeded, So if all of these are successful, so then we can update the status as successful and proceed to commit, and we can follow along, like we can release the memories or the descriptor and we can reclaim. And if it fails, then we can set the status as fail, and we have to roll back and abort the progress. So in this work, Goriwi, they have used the process to defer the reclamation process, so that we can get some efficiency. For example, think about it. When we are trying to claim the memory locations of 3 words or n equals to 3, in this work we are thinking the n as k. So my k is equals to 3 actually. So we need at least k plus 1 instructions to update the 3 locations. Because you can see, like, when we are trying to claiming the words, we are using 3 cases. So we can update the old values with the new word descriptors. So here I have 3 cases. So k equals to 3, we can think. And we need 1 more case to update the descriptor status from active to successful. So that is k plus 1 that we are saying, like, we have to use k plus 1 case instructions to update per k number of words. If I have 5 words, we need 5 plus 1.
The question, I remember you the reclaimer phase.
Yeah.
Have another 3 cast operations.
Yeah. So we are not counting them because we are doing them when my CPU has some idle time, or we are doing another MCAS operation, calling another MCAS operation, because we are deferring this process.
Oh, yes.
So this is the trade-off that we are doing in this work. So that's why we are getting k plus 1 number of cases efficiency instead of the previous other algorithms, which had 2k plus 1 or more of the case operations.
Yeah, while the reader writer.
So here the threads are only reading, not writing.
Not only read, not write. Okay.
Yeah.
But the other methods have
I'm going for the last one again. Yeah.
Other methods have
Yeah, some of them have the read and write both process.
Most efficient one should be 2k plus 2, 2k plus 1, and it has a read write. Yeah, there's a 2k plus 2. Yeah, this is most close to our current work.
Yeah.
But it has a reader's write.
Yeah, but this is the trade-off. Like this one, we are thinking about the efficiency. So, yeah, to have this, we have to have the k plus 1. We have this readers. It's not right.
Yes, the current work is the most efficient ones.
Yeah.
Less cast and no readers write.
Yeah.
Good.
Now let's talk about the thread helping process, because we are talking about the multi-threaded environment and we are not blocking the processes. So maybe the other threads can help each other. So let's see how the thread helping can happen here. So if we go back on our code again, we can see, like, when we found this is a word descriptor, the thread should check if this is a parent word descriptor or not. And then it should check the status of the MCAS descriptor table. If we find, like, the MCAS descriptor table is not successful, its status is active, so maybe the previous thread that was working on it, maybe it's busy or it's stalled. So then the new thread can help the previous thread to complete the process, and it can call the MCAS process, MCAS parent process again. Now let's see how it can work here. So here is my initial values again, and you can see here we have 2 threads. We are thinking about only 2 threads here to make this thing simplified or easy to understand. So at T0 time, maybe the thread 1 is having this MCAS descriptor table, and it has already acquired 2 of these locations, like apple and banana. They have it has updated these 2 locations with the word descriptor. But before it go for the third one, maybe this thread is stalled or busy for other reasons. So in that case, if thread 2 is coming here at T3 or any other timing, it will read the 1001 locations. It will start from here, and it will see there is a word descriptor because it has been updated by thread 1. So when it is see there is a 1001 has a word descriptor, it will go for the MCAS descriptor table, and it will see that the MCAS descriptor table has the status is active. So that means the previous thread was already working on it. So it will call the MCAS parent process again, and then it will complete the process for T1 or the thread 1. So when the whole process is done, it can finalize the descriptor and it can update the status is as successful. So
question, does it mean the thread 2 must check apple, banana, the cherry one by one?
Yes.
Until find the cherry is not yet.
So for the first one, when it is see like this location has instead of apple, this has the what descriptor, it will go in this table, right? And it will try to pick the old value or the new value according to the status. So when it is see its status is successful, then it can pick the new value. But because it's active, so it will see like it's active, so that means it should call the parent MCAS.
That's why the thread 1 only in the status of active.
Yeah.
Thread 2 can help.
Yeah.
Is that possible? Thread 2 can directly jump to the third one, skip the first and second ones.
To ensure the atomicity and connectiveness, it should complete the whole process again because it's following the parent MCAS process.
Okay. Yeah, we can do some optimizations here. Directly go to the third one. That one need help. All the other artifacts don't need help.
Okay.
Suppose for example, the MCAS, the M is so large. In this example, 3. How about the 10? We can don't check there. Directly go to that one need help.
So because when thread 2 is coming here, if it says like this one is updated with the word descriptor, if it jump to theory, maybe there are, suppose for example, we don't have only one, maybe we have 5 locations, and maybe some of them are updated by the thread 1. Okay. If it doesn't check like which one is updated, like what I'm trying to say, like maybe I have 5 locations, we still need to go forward to check where it should start the updating process, right? So still we are reading. So that's the process. Like we have to start from the MCAS beginning.
That's great. That's great.
We cannot. I don't think we can optimize here.
Good argument. Yeah.
So in this work, Goriwi et al., they have shown some experiment with some hardwares with some basement with some base algorithms. So we can see they have used the hardware Intel Xeon, which contains 40 threads, and the benchmark was tested per test runs for 5 seconds, and they have run at least on an average 5 runs. And they did this work for array benchmark and doubly linked list, we will see. And in this,
can you explain what is a dual processor? dual processor, the hardware.
The 2 processor.
2 processor.
Yeah.
Does it affect the performance? 2 processors. Does it 2 processor?
It should, because
2 processor will connect with all 2 processors will connect to the memory.
Yeah.
And the 2 processor cannot share the cache. That may affect the performance. Yeah.
So in this test, they have compared the AOPT, that is the new proposed algorithm, and PMWCAS, which is persistent multi-word comparant sub, and its volatile version was checked as the baseline algorithm. Now, the thread performs MCAS-based read, modify, and write operations on random memory locations here. And there are 3 different array size was tested in this process. So for arrays 10, 100, and 1000. And these horizontal lines, these are representing the number of threads, and the vertical axis. And the vertical axis is they are holding the throughputs, like millions of operations per second. Now, here with the green dots, we are representing the AOPT, and with the orange, we are representing the persistent multi-word comparance of the base algorithm. Now, what is throughput? So the throughput is the number of successful operations per second, and it's good when it's higher. So we can see in our observation, we can see like these are always higher than the baseline algorithm, the PMW CAS. So it's the AOPT is outperforming the PMW CAS always.
Can you explain why as array size is 10 is a decrease so much? The left side.
Because AOPT requires like pure CAS operation. We saw like only K plus 1. And on high contention, it's performing like this.
So when the array size is 10, so our MCAS doesn't work very well. Yeah, the throughput will decrease sharply with the number of threads. Yes.
Now let's talk about the helping ratio that we have seen. Like when we have multiple threads, we can help. They can help. So here is the three diagrams, three figures for the RSS 10, 100, 10,000. We can see the helping ratio is denoted with the vertical axis. Now the helping ratio is good. We can say this one is good when it's lower because we need less help to complete the process. So what is our key observation here? We can see like the AOPT is working good than the PMW CAS. Now let's see the same thing for the doubly linked list benchmark. So in our doubly linked list, we have our threads operated on a shared ordered of state in our doubly linked list. And we can see here we had 3 different list sizes for 5, 50, and 500. So here again we have denoted the green dotted for AOPT and the orange dots for PMW CAS. So what is our observation from this one? So here we can see the AOPT is always performing good in high contention, like it's almost 2.6 times faster or 2.2 times faster in our list size 5 and 50. But when its list size is 500, it's doing a little bit better than the PMW CAS. So why? Because AOPT has the lower CAS complexity and has pure interaction, which has the in high contention cases like this one. But in other case, PMW CAS has the faster diff. Now here we have some future works that we can think about it. The first one is optimizing the read performance. We know like for now when a process is complete, we are deferring the reclamation process. So in that case, when a read operation is coming through, like for example, if we try to read a complete or the successful MCAS descriptor table. So then when a new thread is coming, it's going for the read process in a specific memory location, and then it's going through the MCAS descriptor table, and it will see it's successful. Then it will pick the new value. So this can introduce a read overhead. So instead we can clean up the location with a new value. Like for example, if a new thread see like there is a word descriptor, instead of going through all of the processes, maybe it can update the word descriptor with a new value. So on next cycle, when a new thread will come through, it will see the new value. So it will not have to go through again for the long read processes. So that is one way we can optimize the read performance. The second one is smart release or release for the memory for the descriptor. So right now we are waiting for the lazy time of the CPU or for the next call of MCAS. What will happen if we don't have so much frequent of MCAS call? So we will end up having a MCAS descriptor table for a long time. So instead of waiting for that long, maybe we can do some other ways. Like we can use a reference counter, or we can use a versioning process. So if we see like we already have a few number of MCAS operation is completed, maybe we can reclaim the memory. So this can be used to optimize the memory management. The last one, we can use the MCAS process for other kind of algorithms. For example, the parallel SSD decomposition. So here is my all of the references.
Good work. Good work. Can you back to your future work?
Yes.
Can you explain what is parallel ICC decomposition? Why your MCAS can apply to here?
Because this is a parallel processing, and these are some other algorithms. This is my future work. I have not explored yet, explored this yet. So I'm just thinking to use this MCAS process for other algorithms.
Because this is a parallel ICC decomposition.
Yeah.
They have the concurrent data structures like this, but they simply implement by using logs. Using logs, the busy check log. Like they can use CAS to implement the log. So it's not efficient. Then we can try to use our MCAS to replace the log. Yeah, that's a good future work.
Okay.
This can be our testing benchmark.
Yeah. Okay. So, any more questions?
Great.
This seemed pretty clear to me. So I'm not familiar with a lot of the parallel stuff, so it's a little hard to form questions on that to begin with. Other than the baseline stuff was covered rather effectively, I think, at least.
If there's no other question, that's for today's presentation.
Thank you.
Okay.